Hello, this is Dr. Vev, and in this video I'd like to explore a little bit more about the connection, the intimate connection between the center of mass and momentum, particularly the conservation of linear momentum. Let me recall some basic definitions. The center of mass coordinate for a system of particles, discrete particles, is the sum over all I values of mi times ri, where each ri represents the position vector of the ith particle, divided by the sum of all the masses. I like to call the sum of all the masses the total mass, capital M. So we have our basic definition, which we saw some videos back. Now this I can multiply on both sides by capital M to get M times RCM is equal to the sum of mi ri. If I differentiate both sides, take d by dt on both sides, then I end up getting mass times the velocity of center of mass is equal to the sum of the mass mi times the velocity vi of each of those masses. Now recognize what this actually means. This tells us that the momentum of the center of mass must be equal to the sum of the individual momenta. So that's a pretty powerful statement. You can just keep track of the center of mass, and that will give you an idea of how the system evolves. Now in particular, if you have a situation in which there's no force acting in the system in at least one direction, so if sum of external forces in the jth direction is 0, that j means the jth direction, then I have the initial momentum, center of mass momentum, in the jth direction is equal to the final center of mass momentum in the jth direction. Now the jth direction can be something like x or y. Let's take an example. It's best to study this using examples. Let's take an example that you may have experienced in real life. So you walk from one end of a boat to the other end of the boat. Now if the water is really still, you will observe that the boat moves back. So that's the canoe problem. So you have a canoe here. Let's call the mass of the canoe capital M, and the mass of the person little m. So the length of the canoe is L. The canoe, being uniform, has got a center of mass exactly in the middle. So let's just assume that the person and the canoe are such that the canoe's center of mass is somewhere here. The center of mass of the system is somewhere here, where I put the star symbol. Now we want to find, if this person moves from here to here, how much will the canoe move back? So let's call this distance x, and then that distance is going to be L over 2 minus x. And this entire distance from here to here is going to be L minus x. So that's the situation. Now when the person moves completely from left to right, we have to ask ourselves, are there any forces along the x direction? Along the x direction, the only force you can think of is the friction due to water. Well, if that frictional force can be neglected, then the canoe will experience no force in the x direction. So we can conserve momentum in the x direction. But the initial momentum was 0, so the final momentum also has to be 0. In other words, what I'm saying is that the canoe is going to move backwards and situate itself in such a spot that the location of the final center of mass of the canoe will be exactly where the initial center of mass was located. So this part does not change its location. Okay, so that's what I'm saying. Now by symmetry, if that is the case, then the positions x, so the person's final location is here, it's come to the front of the canoe is moved back, but the canoe is moved back so that this, if this was a glass bottom boat, you will see that the center of mass has not moved. Okay, so the canoe has to move back such that the star remains in the same position. So that's L minus x. And so the total displacement of the canoe from this picture is pretty clear. It's going to be L minus x minus x. So the displacement of canoe, which I'll call delta, this distance here, is just L minus x, or L minus 2x. So all I have now got to do is find x. Well, x is the location of the center of mass from where the person is standing. Let us use the origin at the point star. So 0, which is because the center of mass is at the origin, is going to be a negative m times x plus positive capital M times L over 2 minus x divided by the total mass. So that's the definition of the center of mass I'm using for the x direction. The reason for this is that the person is located at negative x. If the origin is at the point star, then the person's location is negative x, and the boat's center of mass is located to the right at L over 2 minus x. So if that is 0, then I have to have the equation that mx must be equal, numerator is 0, so that's going to be mx equal to m L over 2 minus x. Let me simplify this. That gives me ml over 2 minus mx. I will add mx to both sides, so I get m plus m times x is equal to ml over 2, which tells me that x must be equal to capital M over m plus m L over 2. Let's pause to see if this makes sense. If the person is extremely light, then m is nearly 0, so m over m will cancel out, and you get the center of mass is located exactly in the middle of the canoe as it should be. So that looks good. All right, now the canoe movement delta, therefore delta is equal to L minus 2x. If I do L minus 2x, I get rid of that 2. So I'm just going to get L multiplied by 1 minus m over m plus m. Now when I work the common denominators, which I'll do in the next step, I'm going to get m plus m minus capital M over m plus m. You'll notice the capital M cancels out, and so I have little m L over m plus m. So that's the distance the canoe moves. That's the answer to our problem. Let's test it out for two limits. If the person has got very little mass, then m is close to 0 and the canoe doesn't move. That makes sense. On the other hand, if the person is really massive and the canoe is super light, like made of balsa wood or something, then the capital M is 0, and so the canoe is going to move the entire length back. That also makes sense. So that's that problem. Problems of this sort are intimately related to momentum conservation. In this case, the initial momentum is 0, the final momentum is 0, so the center of mass stays put and does not budge. In the next problem, the center of mass does move, but in the middle of a process, it's interrupted. So let's look at this famous class of examples. So you have a projectile that starts out, like all projectiles do, with some initial velocity v0 at some angle theta, and then if nothing had happened, this projectile would have simply gone in a parabolic trajectory and ended up hitting the ground at some distance, which I'm going to call the full range L of the projectile. Okay, that's its story. You can actually find out the full range rather easily, so let's take some trouble to do that. The time taken to reach the highest point is got by setting the y velocity equal to 0. So let's find out that time. So that time is equal to the y velocity, which is going to be v0 sine theta over g. So the y velocity at the top is 0. That gives you the time of flight up to the top equals that. So the total time of flight, capital T, is going to be 2 times that. So the range, which is L, is just going to be the x velocity, which is v naught cosine theta times the entire time t. So that's going to be 2 v naught. There's a v naught here, there's a v naught there. So it's 2 v naught squared sine theta cosine theta divided by g. So just keep these formulas in mind. Now what I'm going to say that at the highest point, the projectile one day explodes into 2 fragments. At the highest point, you know that the velocity is entirely in the x direction. In fact, the initial velocity will be v naught cosine theta because the only the x component survives at the highest point. So to make this problem more interesting, what I'll say is that at the highest point, it splits into 2 equal fragments. I'll draw the projectile a little bit big. So I get m over 2 here and m over 2 there. And then this one fragment simply drops straight down. The question is, where will the other fragment land? So you'll expect the other fragment to land a little bit further out, but exactly where? So this problem can be solved using momentum conservation rather simply. First of all, observe that the time taken for the projectile to go up is the same as the time taken for it to come down. So this will take the time equal to little t, and that will also take the time equal to little t. But this one is falling straight down. So we have to apply momentum conservation at the highest point. The sum of the initial momenta, pix, is equal to the sum of the final momenta, pfx. So the initial momentum is just the entire mass of the shell times v naught cosine theta, because that's the speed at the highest point, is equal to 0 because the first fragment simply drops dead. And then the second fragment is m over 2 times unknown velocity v. So this unknown velocity v. Let's find out what that velocity is. Cancelling m from both sides, I get v equals 2 v naught cosine theta. So it goes at twice the horizontal speed. So if it goes at twice the horizontal speed, then in the time t it requires to fall down, it'll cover a distance. The new distance, let's call this distance x. The new distance x is going to be the speed v times the time t for it to fall down. And that's going to be 2 v naught cosine theta from here for capital V. And for t, the time taken to go down, which is the same as the time taken to go up, is v naught sine theta over g. But observe what this is. This is equal to the range, L. So we have this astounding result that x is equal to L. Now, let's actually see if that makes sense. L is the normal range of the projectile, and I'm saying that this the half range is L over 2. So if one fragment falls at L over 2 distance, the other fragment, it is calculated, falls over there. So in other words, this is L over 2. Well, does that make sense? It certainly does, because the center of mass has not changed its motion. The center of mass continues in its original parabolic trajectory. That's the whole point. At the highest point, x momentum is conserved, so the center of mass proceeds as though nothing had happened, and center of mass hits the spot. And you can see that it's true, because if the center of mass location is here, then m over 2 times L over 2 on this side must be equal to m over 2 times L over 2 on this side. So the center of mass exactly occurs here. So we conclude, therefore, the center of mass continues unaffected. Well, it doesn't mean that a person standing at the location of the center of mass will feel anything, because one portion of the shell lands here, the other portion lands there. The person standing there is going to be unhurt, but the invisible center of mass is still going to impact that point.